Welcome back, everyone, to our ongoing deep dive into the OEIS.
Yeah.
Today, we're looking at sequence A000156.
Okay.
And this one, it might seem a little esoteric at first glance.
Right.
It deals with a number of ways to express an integer as the sum of 24 squares.
Wow. 24 squares. That's a lot.
Yeah, you heard that right? 24 squares.
Oh, but what's fascinating is that this isn't just some arbitrary mathematical curiosity.
Yeah.
The choice of 24 is deeply connected to some pretty profound concepts in number theory.
Okay, so let's unpack this a little.
Sure.
We're taking an integer, like, say, 5,
Right.
and figuring out how many different combinations of 24 squares add up to it.
Exactly. And you can imagine the number of possible combinations
Yeah.
grows pretty rapidly as the integer increases.
Oh, wow.
The sequence starts with 1,
Okay.
then jumps to 48 for the number 2,
Okay.
then 1104 for 3.
Wow.
It's a testament to the hidden complexity lurking beneath seemingly simple mathematical ideas.
So we're not just talking about simple addition here. There's a lot more going on under the hood.
Absolutely. The formulas used to calculate these terms
Okay.
involve some pretty advanced mathematical machinery,
Got it.
including concepts like Ramanujan's tau function
Right.
and sums of divisors raised to the 11th power.
Now, I remember Ramanujan's tau function from my number theory courses,
Of course.
but I'm having trouble seeing how it fits into all of this.
Yeah.
Can you shed some light on that?
Sure. One of the formulas used to generate the terms of this sequence
Okay.
actually utilizes the tau function,
Go.
which is this incredibly versatile tool in number theory.
Yeah.
What's remarkable is that this formula
Yeah.
essentially links the world of sums of squares to the world of modular forms through the tau function.
Okay.
It acts as a kind of bridge between these seemingly disparate concepts.
So we're talking about modular forms.
Yes.
Those are functions with those amazing symmetry properties, right?
That's right.
The ones that show up all over number theory.
And the fact that they emerge in this context hints at a much deeper level of structure
Great.
within this sequence than might be apparent at first glance.
Wow.
The formula provides a concrete computational link,
Okay.
allowing us to calculate the terms of the sequence using values of the tau function.
That's incredible.
Yeah.
So
Yeah.
we're not just dealing with a list of numbers here,
Right.
but with a sequence that touches upon some of the most fundamental concepts in number theory.
Absolutely.
What about this other formula? You mentioned the one with the divisors.
Right.
How does that work?
That formula dives into the world of divisor functions,
Okay.
which, as you know,
Yeah.
tell us about the divisors of a given number.
Right.
What's remarkable about this particular formula
Yeah.
is that it uses the sum of the 11th powers of the divisors.
Wow.
It's a way of extracting information about the structure of a number
Right.
through its divisors and then connecting that information to the number of ways it can be expressed as the sum of 24 squares.
It sounds like we're just scratching the surface here. This seemingly straightforward question about sums of squares
Right.
has led us to modular forms, divisor functions, and the tau function.
It has.
What else is hidden within this sequence?
Well, for starters, there's another formula that involves a recursive approach,
Okay.
where we calculate a term in the sequence based on the values of previous terms.
Okay.
This particular recursive formula actually links our sequence,
Yeah.
A000156,
Right.
to another sequence in the OEIS,
Okay.
one that deals with the representation of integers as the sum of 12 squares.
So it's like these sequences are all interconnected,
They are.
forming a sort of web of mathematical relationships.
Yeah.
That's fascinating. Can you give us a sense of what this recursive formula looks like?
Sure. One version looks like this. A of n equals 48 over n times the sum from k equals 1 to n of A18669 of k times a of n minus k with the a of 0 equals 1.
Okay.
You can see that to calculate the nth term,
Yeah.
we need to know the values of all preceding terms,
Right.
as well as corresponding terms from the sequence for sums of 12 squares.
It's almost like building a tower, brick by brick,
Right.
where each level depends on the ones below it.
Yeah,
It's a powerful way of thinking about generating these complex sequences.
it is.
But I'm still curious about that connection to modular forms.
Okay.
What can you tell us about that?
Right. Well, to really appreciate that link,
Yeah.
we need to talk about generating functions.
Okay.
Essentially, the generating function for our sequence.
Oh.
The one capturing the number of ways to express integers as the sum of 24 squares can be expressed in terms of a specific modular form.
Hold on, just a quick reminder.
Sure.
What exactly is a generating function again?
Yes, good point. It's like a compact code for the entire sequence,
Okay.
a power series where each coefficient corresponds to a term in the sequence.
Okay, that's coming back to me now.
Good.
So that this generating function, which encapsulates all the information about our sequence,
Yes.
is tied to a modular form,
Yeah.
one of those functions with the remarkable symmetry property.
Precisely. And because of that connection, we can leverage the powerful theory of modular forms
Okay.
to probe the deeper structure and properties of our sequence.
Wow.
It's a beautiful example of how seemingly disparate areas of mathematics can come together to illuminate a problem.
It's like we're using different lenses to examine this sequence,
Right.
each revealing new facets of its complexity and beauty. But before we get too carried away,
Sure.
I think it's time to wrap up part 1 of our deep dive.
A good place to pause indeed, but this is just the tip of the iceberg.
Right.
There's so much more to explore with this fascinating sequence. And we're back, continuing our exploration of OEIS sequence A000156.
Right.
This intriguing sequence that tallies the ways to represent integers as sums of 24 squares.
We've already encountered modular forms, divisor functions, and even a recursive formula
Right.
that connects this sequence to another one dealing with sums of 12 squares.
Yeah.
It feels like we're uncovering a hidden network within the world of numbers.
It's a beautiful web of connections indeed. And there's still more to uncover. Each formula we've discussed provides a unique perspective,
Okay.
a different lens through which to examine the sequence.
You mentioned earlier that the formula involving Ramanujan's tau function hints at something deeper about the structure of this sequence.
I did.
Can you elaborate on that?
Absolutely. The appearance of modular forms here is a significant clue.
Okay.
It suggests that this sequence might be more than just a list of numbers.
Right.
It might be encoding information about deeper mathematical structures.
Okay. That piques my curiosity.
Yeah.
What kind of information could a sequence like this encode?
Sure.
And how do modular forms come into play?
Well, remember that modular forms are these special functions
Yeah.
defined on the complex plane possessing remarkable symmetry properties.
Yeah.
They pop up in various areas of number theory,
Yeah.
and their presence often signals deep underlying structures.
Right. We talked about those symmetries earlier.
You did.
But how do they relate to the actual terms of our sequence?
Think of it this way. The formula connects the number of ways to express an integer as the sum of 24 squares
Okay.
to the value of a specific modular form at a particular point.
Right.
It's like the modular form is acting as a sort of blueprint,
Okay.
and the sequence is a manifestation of that blueprint in the realm of integers.
So it's not just that we can use modular forms to calculate terms.
Right.
It's that the sequence itself seems to be governed by the properties of these forms.
Oh, it's that.
That's really thought-provoking.
It is.
But we've also touched upon another intriguing concept,
Right.
a recursive formula that ties this sequence to one for sums of 12 squares.
Yes, that connection highlights the interconnectedness of sequences within the OEIS.
Right.
They're not isolated entities, but rather nodes in a vast network of mathematical relationships.
Right.
And this particular connection suggests that there might be a deeper relationship between sums of squares for different numbers of squares.
That makes sense. After all, we're dealing with squares in both cases.
Right.
It wouldn't be surprising if there was some underlying mathematical structure connecting them. Could you remind us what that recursive formula looks like?
Sure, it's A of n equals 48 over n times the sum from k equals 1 to n of A1866690 of times A of n minus k, where A of 0 equals 1.
Right.
Notice how we're using terms from sequence A1866690,
Okay.
which deals with sums of 12 squares,
Right.
to calculate terms in our sequence for sums of 24 squares.
It's like a mathematical recipe where the ingredients for one dish are used to create a completely different dish.
Right.
It's quite elegant, actually, but I'm also wondering about the practical implications of all of this.
Okay.
Does knowing the number of ways to express an integer as the sum of 24 squares have any real-world applications?
That's a question that often comes up with pure mathematics.
Right.
While there may not be immediate direct applications in fields like engineering or physics,
Okay.
the study of sums of squares has had a significant impact on other areas of mathematics.
Can you give us some examples? Where does this seemingly abstract concept show up in a practical way?
Well, for instance, the theory of sums of squares is intimately connected to the study of quadratic forms, which
Yeah.
have wide-ranging applications in number theory, cryptography, and even physics.
Oh, wow.
The insights we gain from studying sums of squares
Right.
can be applied to solve problems in these seemingly unrelated fields.
So it's like we're building a foundation of knowledge here.
Exactly.
And that foundation can be used to construct all sorts of interesting structures in other areas of mathematics.
Right.
It's a reminder that even the most abstract mathematical explorations can have unexpected consequences.
Precisely. And this is just one example. The study of sums of squares has also influenced areas like algebraic geometry and analytic number theory.
Wow.
It's a testament to the interconnectedness of mathematics
Yeah.
and the power of pursuing knowledge for its own sake.
We've explored this sequence through various lenses,
Right.
formulas, connections to other sequences, even potential applications. It feels like we've only just begun to unravel its secrets.
Yeah, you're absolutely right. And this brings us to another fascinating aspect.
Okay.
The connection to lattice points in higher dimensional spheres.
Yeah, that sounds intriguing.
It is.
I'm picturing spheres and grids, but I'm having trouble seeing the link to our sequence. Can you shed some light on that?
Of course, imagine a 24-dimensional space
Right.
with a sphere centered at the origin. Now consider all the points within this space whose coordinates are integers.
Right.
These are called lattice points.
Okay.
It turns out that the number of lattice points that lie inside a sphere of a given radius is closely related
Okay.
to the number of ways to express the square of that radius as the sum of 24 squares.
Wait, so our sequence is essentially counting lattice points inside these high-dimensional spheres.
It is.
That's a pretty mind-blowing connection between geometry and number theory.
Isn't it remarkable? It highlights how a seemingly abstract concept, like the number of ways to express an integer as a sum of squares,
Right.
can have a visual geometric interpretation.
Wow.
And this interpretation can provide new insights and ways of thinking about the problem.
It's like we've taken this abstract sequence and given it a concrete visual representation.
Yes.
It's a powerful example of how different areas of mathematics can illuminate each other.
They can.
But before we delve too deeply into the geometry,
Sure.
I think it's time to wrap up part 2 of our deep dive.
An excellent suggestion. We've covered a lot of ground, but there are still some fascinating avenues to explore.
Right?
Join us for the final part of our journey as we continue to delve into the mysteries of OEIS sequence A000156.
And welcome back for the final leg of our journey into the depths of OEIS sequence, A000156.
Yeah.
We've been on quite a ride exploring formulas, connections to other sequences,
Right.
and even dipping our toes into higher dimensional geometry.
It's been a fascinating exploration, hasn't it? We've seen how this seemingly simple sequence,
Yeah.
dealing with the number of ways to express an integer as the sum of 24 squares,
Right.
opens up a window into a rich and interconnected mathematical landscape.
We ended the last segment by touching upon this intriguing connection to lattice coins inside spheres in 24-dimensional space.
We did.
It's a bit mind-boggling to visualize,
It is.
but it highlights how a problem that appears purely number theoretic can have a geometric interpretation.
It's a beautiful example of the unity of mathematics, often different branches of math,
Right?
like number theory and geometry in this case,
Yeah.
can illuminate each other in unexpected ways.
So how exactly does this lattice point idea work?
Sure.
Could you walk us through it a bit more concretely?
Certainly imagine a sphere in 24-dimensional space,
Okay.
centered at the origin.
Right.
Now picture a grid extending throughout this space,
Okay.
where each point on the grid has integer coordinates.
Right.
These are our lattice points.
Okay, I'm trying to wrap my head around a 24-dimensional grid,
Yeah.
but I think I'm following so far.
The key insight is that the number of lattice points that fall inside this sphere is directly related to the number of ways to express the square of the sphere's radius as the sum of 24 squares.
Okay.
It's like each lattice point corresponds to a unique way of representing that squared radius as a sum of squares.
That's incredible. So our sequence, which we've been exploring through formulas and algebraic relationships,
Right.
can also be visualized as counting these lattice points within a high-dimensional sphere.
Exactly.
It's like we're seeing the same concept through two different lenses, a numerical lens and a geometric lens.
And that's one of the things that makes this sequence so fascinating. It sits at the intersection of different mathematical ideas,
Yeah.
bridging seemingly disparate concepts.
It's a reminder that math isn't just a collection of isolated topics,
Right.
but a richly woven tapestry where ideas connect and inform each other in unexpected ways.
Yeah.
But Before we lose ourselves completely in the abstract, I'm curious about the bigger picture.
Sure.
What are the implications of all this? Does knowing how many ways to express a number as the sum of 24 squares have any real-world applications?
That's a question that often arises when exploring pure mathematics, and while the immediate practical applications
Yeah.
might not be as apparent as in, say, physics or engineering,
Right.
the impact of this kind of research can be profound and far-reaching.
Could you elaborate on that? Where might these seemingly abstract ideas have an influence?
Well, for starters, the theory of sums of squares has deep connections to other areas of mathematics,
Okay.
like quadratic forms,
Yeah.
which show up in cryptography, coding theory, and even physics.
Oh, wow.
The insights we gain from studying one area can often be applied to solve problems in seemingly unrelated fields.
So it's like we're building a foundation of mathematical knowledge.
Yeah.
And that foundation can support all sorts of structures in other areas of math and science.
That's a great analogy. And beyond the specific applications,
Yeah.
there's also the intrinsic value of expanding our understanding of mathematical structures. The pursuit of knowledge for its own sake
Right.
is a fundamental human endeavor, and it often leads to unexpected breakthroughs down the road.
It's a reminder that we shouldn't limit ourselves to thinking only in terms of immediate utility. Sometimes the most valuable discoveries arise from pure curiosity and the desire to understand the world around us.
I couldn't agree more. And in the case of this sequence,
Yeah.
we've seen how that curiosity has led us to a fascinating web of connections,
Yeah.
weaving together formulas, geometric interpretations, and links to other mathematical ideas.
It's been an incredible journey exploring OEIS sequence, A000156.
It has.
We've learned about its properties, its connections to other areas of math,
Yeah.
and even its potential applications.
And remember, this is just one sequence out of hundreds of thousands in the OEIS.
Right.
Each sequence has its own story to tell, its own secrets to uncover, and its own connections to reveal.
It's like we've glimpsed a vast interconnected universe of mathematical ideas.
Yeah.
And this sequence has provided us with a fascinating entry point.
It's been a pleasure exploring this corner of the mathematical universe with you.
It has as well.
And I encourage everyone listening to dive into the OEIS and embark on their own explorations. There's a world of wonder waiting to be discovered.
On that note, we wrap up our deep dive into OEIS sequence 000156. Keep those mathematical minds curious and those calculators handy. And until next time, happy exploring.